Questions about anything? Well, I promised today that I would demonstrate everything you ever were told about the exponential function using very minimal effort. So last time I defined the classic partial sums of the series for the exponential function. So En of x is the sum as k goes from 0 to n of x to the k over k factorial, the famous Taylor series for the exponential function. And last time I showed, just using very elementary estimates, that those functions are uniformly Cauchy on closed intervals, arbitrarily big closed intervals, minus r to plus r, where r could be, think of r as something big. And we learned in 8.1 and 8.2 that a uniformly Cauchy sequence converges uniformly. And so we know that sequence Enx converges uniformly to something. We'll call that something E of x. That's going to be the exponential function that we're going to study. We also know that uniform limits of continuous functions are continuous. So we know that E of x is a continuous function. And it was easy to deduce last time. If you integrate En of t dt from 0 to x, well then when you integrate x to the k, an x to the k plus 1 over k plus 1 comes out. And so that would turn the k factorial to a k plus 1 factorial and the power to a k plus 1. And when you write out that integral, you realize that basically you're getting the next function, except for the constant term. The constant term doesn't come out, and you have to add the constant term. And that's why there's a 1 here. So that's a simple identity. And when you combine it with things we've learned recently, so for example, this side is differentiable. Let's see. Because of uniform convergence, so uniform convergence implies when I take the limit on both sides here, this side, left side, would tend to E of x. And we know that when the ENs converge uniformly to something on an interval, the integral converges to the corresponding limit function integral. Okay, and that's an exciting thing to look at. All we know is that E of x is continuous. But notice that this right-hand side is differentiable by the fundamental theorem of calculus. And so the left-hand side is differentiable, which means E of x is differentiable. So we conclude that E of x is differentiable. And furthermore, and the fundamental theorem of calculus shows that the derivative E prime of x would be the derivative of 1 plus the derivative of that integral from 0 to x. And the fundamental theorem of calculus says that that's equal to E of x. Okay. So now I'm going to get all let's see, get all the basic facts I want. Let's get some simple basic facts right away. Let's see. The En of x is 1 plus x plus x squared over 2 factorial, etc., x to the n over n factorial. If x is positive, all this junk is positive. This is greater than 0 if x is greater than 0. Oops, I don't want all of it. I just want from here to here. Okay, so we have that when I take the let's see, I have that En of x is greater than 1 plus x if x is bigger than 0. And so now when I take the limit E of x would be let's make it greater or equal to 1 plus x if x is bigger than 0. So that implies that E of x goes to infinity. So basic fact number 1, let's see, basic facts so far. 1, E prime of x is itself two, E of 0 is equal to 1, excuse me. E of 0 is equal to 1 because you put in the En of x's, En of zeros are all 1. So the limit, of course, is 1. So that's because En of 0 equals 1 for all n. And I guess the third one here is that I have E of x is bigger than or equal to 1 plus x if x is bigger than 0. So the limit as x goes to infinity of E of x is plus infinity. That's an easy thing to see. I guess I might as well write it out. The way we've done this, E of x is the sum as k goes from 0 to infinity, x to the k over k factorial. Okay, now I'm going to get some more exciting facts about the exponential. Let's see, last time I told you about that lemma. If f is differentiable on R, and f prime of x equals f prime of x is equal to k times f of x for all x. F being differentiable, of course, implies f is continuous, so that would imply that the derivative of f is also continuous, this equation. And that would imply the second derivative is continuous, etc., etc. So that differential equation would imply that f is infinitely differentiable. That's nice to know. Then the conclusion is f of kx has to be this function we're playing around with. It has to be a constant times e to the kx. I can't help but say to the e of kx. And that c, if you see what that c would have to be, if I plug in x equals 0, you see that the c has to be f of 0. Okay, the proof of this lemma is going to be a snap. It's going to be like a math 262, 266, or wherever you had it, or maybe 366. When you talk about linear first order ODEs. Okay, so what the first order ODE is f prime minus k times f equals 0. In fact, that's a first order linear differential equation with constant coefficients. And not only that, it's homogeneous. The right-hand side is 0. So this is one of the most basic ODEs you study in those courses. And you remember, maybe, the big idea was to introduce an integrating factor. Want an integrating factor to make the left-hand side the derivative of something, u. So you multiply it by the integrating factor, and that'll make the left-hand side equals something derivative. Okay. And maybe I won't, when I teach math 266 or 366, I'd multiply that out and realize what I need to make that. Why don't I do it? What the heck? Let's see. Remember what you get when you do that. So I would multiply this by u times f prime minus kf equals 0, and that would be equal to u times f prime minus ku times f. And that first thing looks like it's the derivative of a product. So if this was the derivative of a product, we would have u times f prime would be equal to u f prime plus u prime f. So I'm comparing these two lines. And when I look at those two lines and realize what I need u prime to be equal to minus ku. And I now have an easy function. I have one of these. I have such a thing. Namely, u equals e of minus kx. That's the exciting thing. Let's see, because I'd use the chain rule, u prime would be e prime of minus kx times d by dx of minus kx. And of course, e prime is itself, so that would be e of minus kx times minus k. Check. So I have an integrating factor that's going to work. So now just do it. Remember what the integrating factor is for. I have f prime minus kf equals 0. I multiply by my integrating factor. That would be e minus kx times f prime of x minus k times e minus kx f of x. So I multiply that by e to the minus kx. Multiply by the integrating factor. And then The reason I did that is because now this is the derivative of something. It's the derivative of the integrating factor times the function f. That thing has derivative 0, so it must be constant. We conclude when something has a 0 derivative, we know from the mean value theorem that it's constant. And we can plug in x equal to 0 to see what that constant has to be. Plug in x equals 0 to see e of 0, e to the 0 times f of 0 is equal to the c. And of course, the exponential at 0 is 1. So we see that c is f of 0. So we're getting somewhere. That's something, part of the lemma we wanted to see. But now I'm kind of stuck. I know that e to the minus kx is 1 over e to the kx. But I'm trying to deduce all those basic facts to justify them. And if you think about it, you think, okay, I'm stuck here. I'm not going to get anywhere. Because this is exciting right here. It looks like if I only knew that e to the minus kx was 1 over e to the kx, I could move it to the other side and I'd be done. But here's a sneaky trick. Stop the proof. I'm going to stop the proof and I'm going to start over using k equal 1 and f of x equals e to the e of x. Then that f of x satisfies the property, so this is going to be, I stop the proof and do it over again, and this time I would have f prime of x equals e prime of x equals e of x. We know that, and that's f of x. So it satisfies the hypothesis of the lemma. And let's see, f of 0 is e of 0, which is 1. So the c that I'm going to get is going to be 1. And now I'm going to get that thing in the box. I'll call it star. That thing in the box is star. I get a new star, which is, let's see, e to the 1x times my f of x is equal to c, which is 1. So let's see, this c is 1. My f of x was e of x. Oops, the k was 1, and this is e to the minus 1 times x. And so the new star tells me, this is the great moment when you realize, aha, I get e to the minus x times e to the plus x is identically 1. Put that in a box. That has big implications. So I get basic fact here. What am I up to? Number 5. Number 5. E to the x never vanishes. If the product of those two things is 1, neither one of them can be 0. So e of x is never 0. And not only that, I'll call this number 6, and e to the minus x is 1 over e to the x. So we've got those. Okay, now that I stopped the proof and did that, let's restart the proof. Go back and continue the proof. Let's see, I got star, and star told me that e to the minus kx times f of x equals c, which is f of 0. And now I know that 1 over e to the minus kx is, now I know that this is 1 over e to the kx. And so now I'm done. I get that f of x is equal to f of 0 times e to the kx. Check. Okay, so that lemma is not hard. It's just sophomore ODE ideas. Okay, so now another basic fact, number 7. I showed you the demonstration last time. Number 7 is that e to the x plus y equals e to the x times e to the y. Okay, so the proof of that is to use the basic lemma, that lemma, and to use f of x equals e of x plus y, where y is treated like a constant. Then f prime of x, by the chain rule, is e prime of x plus y times d by dx of x plus y, which is e of x times 1. No, it's e of x plus y times 1. And that's equal to 1 times f of x. So that thing satisfies the hypothesis of the lemma. And we get from the lemma that my f of x equals f of 0 times e to the 1 times x. And then when you think what that means, let's see, my f of x is e of x plus y. My f of 0, when I plug in x equals 0, is e of y. And when I put all those things in there, yeah, so that you see it right here, f of 0 is equal to e of y. And so that's the fact. E to the x plus y is equal to e of x times e of y. Check. Oh, let's see. That was number 8. Basic fact number 5 is that let's see, e of x is never 0. E to the x is never 0. Let's say I know that already. I know it's never 0. E to the x is strictly positive. Well, I know it's never 0. So how would I show that it's strictly positive? If it was negative somewhere, I would have to think about what happens. Here's e of x. It's never 0. And at 0, it's equal to 1. So at 0, it's equal to 1. E to the x is never 0. If it were ever to go negative, what comes to mind? Anybody? What?
You need something to negative power.
Oh,
You need a negative number to power.
we know e of x is continuous.
It should be 0 in between it.
Yeah, it's the intermediate value theorem. It's never 0. If it were negative here, then the intermediate value theorem implies there would be a 0 between, let's call this spot x naught. Implies e of x has a 0. Between x naught and 0. And that's a contradiction. So of course it can never be negative. It's always strictly positive. Okay, that's number 9. Number 10, let's see, we know that e to the minus x is equal to 1 over e to the x. And e to the x goes to infinity. So this is going to go to 0 as x goes to infinity. And so that means that the limit as x goes to minus infinity of e to the x is equal to 0. Okay. Now another one is that e of x is strictly increasing. We deduced that from the mean value theorem. We know the derivative is positive, and the mean value theorem then shows that something is strictly increasing. So e prime of x is equal to e of x, and that's strictly positive. And we use the mean value theorem to see that that implies that something is strictly increasing. Okay. I think that's pretty much all the facts. But now we also know, let's see. Let's do a graph. Everybody knows the graph of e to the x. It grows like crazy, and it shrinks like crazy. So it dies away real fast over here, goes through 1, and grows real fast. And is strictly increasing. And so we see that e of x maps minus infinity to infinity. Let's see, it maps to positive things, so that would map minus infinity to 0 infinity. And because it's strictly increasing, it's 1-to-1 and onto. And it's differentiable. In fact, it's C infinity smooth. What was that up to, number 11? 12, E is C infinity smooth. Okay. E prime of E, we know that it's differentiable. And then when I differentiate that again, I would get E double prime equals E prime. And then I get E triple prime equals E double prime, etc. Okay. Remember the inverse function theorem. So the inverse function theorem now tells us yields L, think log, natural log, L equals E inverse. And let's see, L would map 0 infinity 1-to-1 onto minus infinity infinity. It would only be defined from 0 to infinity on 0 infinity. And remember, the inverse function theorem yields that inverse exists, and it's differentiable. And we can use the chain rule. If you don't remember the formula from the theorem, and the chain rule yields, well, let's see, E of L of x equals x. When I differentiate that, I would get E prime of L of x times L prime of x equals 1. And E prime is itself, so this is E of L of x. And of course, these things are inverses of each other, so E of L of x is x. And so we get that L prime of x is 1 over x. And since L of 1 is 1, we could play games like we did above. L prime of x equals 1 over x, and L of 1 equals 0. So a fun thing to see is that L of x is the integral from 1 to x of 1 over t dt. That's a fundamental theorem of calculus. And let's see, let's play around with what's the L of x1. Let's do L of y1 times y2 is L of y1 plus L of y2. That's the thing, these y's are positive. Otherwise, logs don't make sense. Let's see, how would I show that? The y1 would be e to the x1 for some x, and the y2 would be e to the x2. And so y1 times y2 would be e to the x1 times e to the x2. I noticed I just stopped writing e of x. And pretty soon I'm going to stop writing L. That's e to the x1 plus x2. And that would be y1, what would it be? Am I done? Let's think. Okay, that's a correct thing to write there. y1 times y2 is e to that x1 plus x2. Aha, so the L of y1, y2 equals x1 plus x2. And x1 is the log of y1. Right. X1 is log of y1. It's the inverse of y1 there. And x2 is the log of y2. Check. Okay. Other things you can deduce. Quick, I think I'm running out of steam to demonstrate every little thing. But it follows from the two things. Follows from e to the x goes to infinity as x goes to infinity. And e to the x goes to 0 as x goes to minus infinity, that the log function L of x goes to infinity as x goes to infinity. This is you just have to sit down and write this out. It just follows very simply from the fact that things are strictly increasing and the corresponding limits. So L of x goes to infinity as x goes to infinity, and L of x goes to minus infinity as x tends to 0 from the plus side. Okay. And so from now on, for the rest of your life, we'll write e of x equals e to the x, and L of x equals the natural log of x. Okay. Well, all of these basic facts let's see, what do the basic facts show? Oh, by the way, this famous thing, e of x plus y equals e of x times e of y. That shows this e is a group homomorphism. E is a group homomorphism of the real numbers, the additive group of the real numbers, to the multiplicative group. See, the addition there is the operation in the group of in the additive group, and multiplication is the operation in the multiplicative group. And exactly that identity there says the group structure is preserved to the multiplicative group of r minus 0. What's that called? There's a symbol for r minus 0. What is it? Well, that symbol works. And of course, the L is the inverse, so that would be, and it's also a group homomorphism. And L, so L is its inverse. And of course, the identity in the groups would be the 0 function for the additive and the 1 function for the multiplicative. And of course, they're exactly mapped to each other by those things. So that's an important algebra thing. And that, if you ever read some expository things, E is the unique differentiable function that does that. If you start maybe it's the unique continuous function that does that too. But if you start relaxing those hypotheses too much, then you run into sort of philosophical issues about what's the most general function that could do that. And it gets pretty fascinating. Kind of gets involved with some of the basic foundations of math, things like the axiom of choice, etc., which are scary. Anyway, if you demand that E be continuous, you're stuck with the exponential. It's the only thing that does that. Questions about anything? Let's see, I'm probably getting sick of all these facts, but so here's a question. What is pi to the square root of 2 power? Well, the basic facts here have shown things like that e to the x plus x plus x plus x p times would be e to the x to the p so the pth root, let's see what I've got. So e to the p, what did I just discover? E to the px equals e of x to the p. And so if I take the, stuff like that. And let's see. If I take the pth root, I would get that e to the px to the 1 over p is equal to e to the x. And stuff like that. And so let's see. Here's what I'm trying to say. So just play around. Also show that the log of x to the r is r log x, stuff like that. X would have to be positive. Let's see, in calculus books, you would do this if r is rational. maybe. And then you would fill that in by continuity. Well, let's see, we don't know what x to the irrational thing is yet. Anyway, it's a fun game to play. I'm getting tired of playing games today. But you would find out that x equals e of L of x okay. So x to the p over q is e of L of x to the p over q and that would be e of p over q to the L of x, and that would be e to the L of x to the p over q and that's what it, let's see, yeah. Oh yeah, I'm done here. So this is true if it's e to the p over q ln of x when p over q is rational. Which you realize, aha, those functions are nice and differentiable and continuous, etc. It's the only way to fill in that function to make it make sense for irrational numbers. So we're forced by continuity to define x to the r equals e to the r log x when r is irrational. And so, in fact, pi to the square root of 2 is equal to e to the square root of 2 log pi. And you can compute that using all the formulas I've been spitting out lately. Taylor series, and that log of pi would be the area under a graph that you could calculate as much as you want to.
Sorry, I don't understand.
Sorry.
My pleasure.
You know who is digging this lecture for some reason. Yeah. That's fun. So let's see if I were going to graph. When I graph x to the r, I'd have x to the r defined for all the rational numbers, and then you realize, aha, to fill it in. Let's see, what is x to the x? I guess I'll draw one last graph today. Famous graph. I graph the exponential function. Looks like that. The log function you would get by reflecting that graph about that line y equals x. So here's the line. Y equals x. And if you reflect that graph about the line y equals x, you get the log function. And this would go through that one. Any last minute questions about anything? Okay, on Monday.